Moving on to the next section, we'll deal with some partitioned matrices, section 3.4. More on partition square matrices, the Schur complement. Okay, so we're going to look at a particular way of partitioning a matrix with an eye towards rank. And in the process, we'll discuss determinants of matrices in terms of this new, it's really a component of a partition matrix that we'll introduce. Okay, so first, suppose A is an n by n square matrix of rank R. We can, as we've seen, take A and partition it, potentially with some rearrangements of rows and columns, more of that later, but partition it into some submatrices, W, X, Y, and Z, where W is an R by R full rank matrix, X is R by n minus R, Y is n minus R by R, Z is a little square matrix as well, n minus R by n minus R. Dimensions as usual, just to guarantee there's no gaps, you know what I mean, in terms of partitioning matrix A. But this full rank partitioning exists. Remember, if we start with an arbitrary matrix A, we might need to permute around rows and columns to isolate a full rank minor matrix. This R by R matrix is given here, submatrix, I guess. Okay. Now, with that done, so A is of rank R, W is also of rank R, then what's happening is WX, the upper half of this matrix, is a full row rank. It's full rank R. And so the rows given by the upper half of the matrix span the row space. Similarly, if we'll look at the left half, the WY part, this is a full column rank R, really all those contributions being made by the W part of that partitioned matrix, but full column rank as well. And so the columns of the left-hand part span the column space of matrix A. Okay, so if we look at the remaining rows, the rows in Y and Z, or the remaining columns, those in the right-hand part, XZ part. First, the rows in YZ can be written as linear combinations of the rows in the top half. Yeah, the rank of the top part is R, the rank of the whole matrix is R, so it must be that when we look at the row space, it's spanned by, actually has as a basis, the first R rows of the matrix, the rows of the part WX, the top half. So the bottom half rows don't contribute anything new, linear combination-wise, to the row space, and it must be that the rows in the bottom half can be written as linear combinations. They're in the span of the rows in the top part. All right, so we want to express linear combinations of the rows of WX in such a way that we produce the bottom part, the rows in the YZ part. This requires a matrix, an n by R matrix, let's call it T, such that we produce the rows in the bottom half, bottom part, I don't know how it's partitioned uniformly or whatever, bottom part I should say, the YZ part equals this matrix T times the top part of the matrix. Okay, so when you multiply a matrix, think of matrix WX multiplied on the left by some matrix T, what you get then is linear combinations of the rows of this matrix WX using coefficients from matrix T. You get linear combinations of the rows. Well, linear combinations of the rows can be, with proper coefficients, chosen to produce this collection of rows. So that's how matrix T is determined. So there exists a matrix T such that multiplication on the left of this upper part of the matrix, the partition matrix, produces the lower part. Similarly, there's a matrix S of coefficients such that if we'll take the left-hand part of the matrix, the WY part, multiply on the left by matrix S. Okay, if you'll do this kind of manipulation, what you get is linear combinations of the columns of this matrix using coefficients from matrix S. We'll choose those coefficients in such a way that those linear combinations of these columns produce the other columns. You know the XZ columns are linear combinations of the WY columns because of the rank and the dimension, therefore, of the column space. Okay, so we can introduce matrices T and S. Give me specific matrices and numbers, and I suspect we can compute these things, but we're going kind of in a different direction. All right, so let's see what that implies about relationships between the how do we get to this? W, X, Y, Z parts. Okay, if we'll multiply here, multiplying partition matrices, I just take this matrix T and multiply it by W and take T and multiply it by X. I could carry it inside. We'll do some manipulations like that shortly. But what that implies is that matrix Y must equal matrix T times W, and matrix Z must equal matrix T times X. Okay, so that matrix equation implies these two equations based on, I kind of want to say they're components, based on their parts, since it's partition matrices. And over here, if we do the multiplication, we'll have to have the first part, X, equal the first part over here, which would be W times S. I could take that S matrix inside. That's a legitimate way to multiply matrices of appropriate dimensions. And so we get X equals WS. Second part, Z equals YS. Okay, so we get these two equations from that second observation. All right. I don't really want to talk about T and S because I'd have to run out and compute them in practice. What we're trying to do is in a presentation of a matrix A where we've got this R by R full rank matrix up here in the upper left-hand corner. See if we can express some of the other pieces. It'll be this piece. We're going to express the Z part in terms of the WXY part. So by having matrix A in this form, it turns out the Z part's determined. That's where we're going. So we've got this batch of equations. So we're going to kind of fiddle around with them, but we've got a goal here. I'm trying to solve for Z in terms of W, X, and Y. It looks like we're going backwards because we've introduced not only W, X, and Y, but also T and S. Okay, well, Z equals T times X. All right, here, X can be written as WS, so we can substitute this in for X to say Z equals T times X, second equation, which equals T times W times S from the third of these four equations. W is full rank. That was the setup. It's rank R, and it's R by R. It's full row rank. It's full column rank, square matrix. So W is invertible. Full rank matrices have inverses. We recently observed that. So from this equation, Y equals T times W, multiply on the right by W inverse, and we'll get T equals Y W inverse. T equals Y W inverse. From this equation, we can multiply on the left by W inverse to get S equals W inverse X. And let's see, we had Z equals Y times S from this equation. All right, Z equals Y times S. S, we can substitute W inverse X, and there you go. We get this Z must be Y W inverse X. We could have done that a slightly different way with a different substitution. We get the same thing. But we get Z equals Y W inverse X. That means that partitioned matrix A, provided matrix A is of rank R and matrix W is an R by R full rank matrix, then whatever happens down here can be written in terms of the other pieces. So this is where we had entry Z, and we just saw Z as Y, W inverse X. So the pattern, we'll have to refer back to this, so we'll give it a name. The pattern is, under those conditions on a partitioned matrix, this piece of the partition must be this matrix times the inverse of this matrix times that matrix. So that's the little pattern on what appears down there. All right, that leads us to a definition. If A is a square matrix partitioned as, okay, so no conditions on matrix A, no comments about rank or anything, only that it's square. And we're going to partition it into 4 parts as given here. We're going to require that A11 be non-singular. Okay. So there's no concerns over A11 having rank equal to the rank of A, like we had above. It's non-singular, must be full rank, it must be square. In fact, we're going to talk about the inverse of it here shortly. So we're requiring this in some sense to contain some of the rank of A, maybe not all of it, maybe all of it, maybe not. But we're having in the upper left-hand corner now a non-singular, so a square full rank matrix. Then we're going to define the quantity Z to be this part, A sub 2, 2, minus A sub 2, 1, A11 inverse times A sub 1, 2. This is called the Schur complement of A11 in this matrix. And what we're doing is taking A2, 2, the lower right entry, and subtracting from it this times the inverse of this times this. A21, A11 inverse, A12. So that little pattern is the same thing we had above. All right. To tie it into the observation above, hey, if A11 is a full rank and it has the same rank as matrix A, then we got the situation we had upstairs. Then what's happening is this A22 entry must be of the form A21, A11 inverse, A12, computation we showed above. And so the Schur complement of A11 in A must be A22 minus that, but A22 equals that. The Schur complement must be 0. It's a 0 matrix, right? Remember, these things represent matrices. So I guess in some crude sense, the Schur complement measures how far a partitioning of this matrix is from the kind of partitioning we mentioned above in terms of having a full rank matrix in the upper left-hand corner that has the same rank as matrix A. All right, so now we're going to look at more general matrices and an idea of permuting around rows and columns. Can be done with multiplication by products of elementary matrices, actually by permutation matrices. We had mentioned before, previous section, I guess, that for any n by m matrix A of rank R, greater than 0, don't consider 0 matrix, there's a permutation matrix, an n by n permutation matrix, E sub pi 1, and an m by m permutation matrix, E sub pi 2, such that you take that matrix A, multiply on the left by that one permutation matrix of the appropriate size, to multiply on the right by the other permutation matrix. Then you can take that matrix A, do these elementary row operations and elementary column operations, and you can isolate, in a sense, the rank of matrix A in that upper left-hand entry. This was the, what do we call it, row equivalent full rank form or something to that effect. We saw this a couple of videos ago. But we're creating this little square matrix B11 that's R by R. It's a full rank. We started with the assumption that A was rank R. So in some sense, we've got all of the rank stuff isolated in the upper left. And all we did was permute some things around. We did that in a proof in the past as well. Okay. Well, When we get it in this form, we know from that argument on the previous page, the thing I indicated with an asterisk, that, hey, if this is full rank and equal to the rank of A, then B22 must be of a certain form. It's this matrix times the inverse of this matrix times that matrix. So this lower right-hand entry must be B21, B11 inverse, B12, as argued in the initial computations. Okay, so we can take this matrix, B11, rank R, same rank as matrix A. So we're going to manipulate this thing for a little while, come up with some alternative forms of it. Let's take that matrix and write it in terms of products of some partition matrices. We can write it as B11, B21, partition matrix times the partition matrix I, B11 inverse, B12. Sure about that? Let's check it. First row, first column, B11 times the identity, first row, first column. There you go. Okay, it's not really rows and columns, it's bunches of rows and bunches of columns, but this is how the matrices multiply. Let me continue calling them rows and columns, even though it's misleading. First row, second column, B11, B11 inverse. That'll leave you with a B12, first row, second column like it's supposed to. Second row, first column, identity will produce a B21. Second row, second column will produce, it produces a B21 times B11 inverse times B12. Oh, but that's what we're supposed to have there, as we saw from asterisk. So we really can write this matrix B, when it's in the appropriate form, in this form. Now we're going to take this and manipulate it a little bit. We're going to effectively factor a B11 out of the first matrix. Can you do that? Does B11 inverse exist? Yeah, B11 was a full rank. Its rank R, it says that somewhere upstairs, there it is. B11 is a full rank square matrix, so it is invertible. Okay, so what we're doing is effectively pulling a B11 out of this first partitioned matrix. Look what happens when you put it back. You get B11 in the first entry, and you get B21 times B11 inverse times B11. You get B21 in that second entry. So the arithmetic holds. Haven't manipulated the second part. Hey, let's manipulate the second part. Let's take that B11 matrix and stick it inside this second partition matrix. So B11 will have, in a sense, first row, first column. There's only first rows. That'll get a B11 entry here. And when I multiply here, we've got this matrix and its inverse, leaving us with the B12. So this matrix of B's can be represented in two different ways. Let's see, it's these two I think we're interested in, where we've got an identity in the right-hand partition matrix, and here we've got an identity in the left-hand partition matrix. Okay, back up to this idea of the original matrix A. We scrolled off the top there, but we took A and we multiplied it by some permutation matrices to produce this thing, this matrix of B's. All right, what we're going to do next is talk mainly about matrix A. Okay, I got this permutation matrix and this permutation matrix in the way. So let's move them to the other side. They're invertible, right? Yeah, all permutation matrices are invertible. So let's define P to be the inverse of this matrix on the left, and define Q to be the inverse of this matrix on the right. So we can take these E sub pi 1s and 2s, move them to the other side of the equation with their inverses. They are invertible. They're permutation matrices. All permutation matrices are invertible. Permutation matrices are products of elementary matrices, so they're invertible. They're not just any product of elementary matrices. They're products of row swaps or column swaps, because we're doing that as well. So anyhow, the inverses do exist. When we move them to the other side, now we'll have A times E sub pi 1 inverse, but we've called that pi, times what we had before, this part, say, times E pi 2 inverse, but we've called that Q. So we take those permutation matrices to the other side using this form of the matrix here. Then let's take the P matrix inside this first partition matrix and the Q matrix inside the second one. So we get P's on, as it were, the entries in the partition matrix, and same thing with the Q's. We don't get any simplification on this one. And let's also look at this version of the matrix of B's and have P times that matrix of B's, but that version of it, times Q, and do the same thing. Put the P inside the first one and put the Q inside the second one. Okay, that gives us two representations of matrix A. Okay, I want to try to have the conversation with all of this in front of us. Let me shrink it a little bit. P and Q are permutation matrices. They're a full rank. B11 is a full rank. So what you got going on here? Well, we've got a full rank matrix times a full rank matrix. And somewhere along the lines, we said implicitly or it's implied, those are both, that product is full rank. Product of full rank matrices is full rank. So we've got, for this partition matrix, we've got a full rank matrix up top. In fact, it's a square matrix. Let's see, B11 is R by R. Matrix P was a permutation matrix. It was actually acting on matrix A, wasn't it? So I'm not sure entirely what the dimensions of the P matrix is, but the product is defined. And oops, I scroll too far down. Okay, so we're looking at this. All right, we got a full rank matrix at the top. Let's look at this as well. P itself, that's a full rank matrix. Okay, so it must be that these two matrices are of full column rank. You know, this is a full column rank, takes care of the columns. The matrix up here, the first one is a full rank, full column rank, say. So that takes care of all the columns as well. So these are two matrices that are full column matrices. Similarly, if we'll look at the other pieces, this piece, hey, Q is a full rank matrix. It's permutation matrix. It's invertible, it's full rank. And same argument, this product is also full rank. So now I want to talk about row rank. For the partition matrices. So this partition matrix is a full row rank, and this partition matrix is a full row rank. So we got full column rank here, full row rank here, full column rank here, full row rank there. So that's where we were going as a goal in terms of that manipulation of those partition matrices. So both of these things here give two factorizations of A of the form A equals L times R, where L is an N by R full column rank matrix, and R is an R by M full row rank matrix. All right, so matrix A wasn't square. These matrices probably aren't square either, necessarily, but we've written A as a product of two matrices that are of a kind of full rank. First one, the one on the left, L, is a full column rank. The one on the right, R, is a full row rank. And such a factorization has a name. We're calling these factorizations. Sometimes they're referred to as decompositions. Factorization is probably a little bit better term because you're writing things as products. But N by M matrix A of rank R, if it can be written in this form, A equals L times R, where L is full column rank and R is full row rank, then A equals L, R is called a full rank factorization of matrix A. Okay. We haven't seen the last of matrix factorization. This is really from the perspective of rank. We might have other perspectives. Might be interested in eigenvalues and stuff, and you'll factor matrices in a certain way that involves diagonalization. That you do in linear algebra. Factorization, that word may not come up, but it's the same idea of taking a matrix and writing it as a convenient kind of product. But our angle here is totally on this rank stuff with an eye towards row rank and column rank. Theorem left as an exercise, fairly easy exercise, I suspect, because it claims that we have an inverse matrix. Well, finding inverse matrices is one thing. Claiming this is an inverse, well, that's easy. All I got to do is multiply it by the given matrix and make sure we get the identity out. So the claim here is if A is a square non-singular matrix, all right, that stuff right there tells you we can talk about A inverse. And if A is partitioned, as we've been partitioning matrices as of late, A11, A12, A21, A22, where both A11 and A22 are non-singular. All right, that makes sense. A is non-singular with an idea towards rank. The rank of A must be, say, the number of columns or the number of rows. Okay, well, that means a linear independence of the rows here, which really means a linear independence of the rows. Whoops, well, let me highlight just the left-hand half. And similarly, since A has rank, is a full rank, then all the columns must be linear independent. So we could calculate the rank by considering a rank of the left-hand half and the rank of the right-hand half. We must have an equality there. So A11 and A22, they'll have to be non-singular as well. Then the claim is, in terms of the Schur complement of A11 and A, to recall that was this thing here. So it's a combination of this, that inverse, and that. Claim is we can write the inverse of matrix A is given here. A inverse is, oh, there you go. It's got A11s, A12s, A21s, and Z's in it. So what's missing is the A22s. But remember, I know A22 as it relates to the others and it relates to Z, the Schur complement. So anyhow, we've simply claimed that we can write the inverse of matrix A in this form. Exercise 313, how are you going to prove that? Yeah, multiply it by this thing on one side and see if you get the identity. And then either multiply it on the other side and see if you get the identity, or quote the appropriate theorems to say, hey, square matrix, only got to check it on one side. We established that earlier in our conversations about inverses of matrices. Okay, a couple of little results, and then we're done with this section. This is a mercifully short section compared to what we've done recently in Chapter 3. Theorem 3.4.2 says, if A is a square matrix such that A is written as the transpose of a matrix X, down here we got the transpose of a vector Y. Over here we've got matrix X itself, and we've got vector Y itself. We would be treating Y as a column vector. I can kind of tell from the context. So over here, Y transpose would be a row vector. We've added, in some sense, an extra column on the right and an extra row to the bottom in terms of this kind of manipulation. Claim is, given X is a full column rank matrix, claim is the Schur complement of X transpose X in A is this thing here. Okay, all we need to do is this multiplication, express A in terms of that, and then compute the Schur complement. So let's watch that happen. Section 3.4, the proofs. Okay. So hypotheses, claim on the Schur complement, piece of cake. You know how to take the products. I guess it's theorem 3.22 that tells you how to do that. Do a row times column thing. So we do indeed get X transpose X in the upper left. X transpose times Y here, Y transpose times X here, Y transpose times Y here. Okay, so there's what we get when we take the product, multiply out, get A in a particular form. Now, Schur complement of X transpose X would be what we'd write as Z, and it would be this inverse, that. That's how you computed Schur complements. They claim the Schur complement is, excuse me, it was this term minus that. I wasn't getting the right thing, so we'll have this minus this times this inverse times that. Okay, and that's exactly what we have. We have the Y transpose Y minus Y transpose X, right, this thing inverse, right, times that thing, X transpose Y. So total piece of cake, just multiply out, and there it is. We actually have another theorem. Let's just take it from here and do the proof. It says if A is a square partition matrix, usual way of partitioning, where A11 is square and non-singular, okay, so A11 in inverse exists, square and non-singular. When you hear non-singular, you think invertible. Well, we had a little bit longer story than that in here, but when the dust settled, non-singular meant invertible, provided we had square matrices. And we're going to take a square matrix, we're going to take a determinant of it. Determinants of square matrices makes sense. And the claim is a determinant of A can be written as the determinant of A11, this part, times the determinant of this thing. Well, that thing there is actually the Schur complement. So the claim is we can take determinants of a matrix, provided this upper left-hand part is invertible, and compute those determinants using the determinant of the upper left part times the determinant of the Schur complement of that upper left-hand part in this matrix. Okay, we need to recall determinant of the product is the product of the determinants, and that's about it. Okay, we've got A written or partitioned in the usual way. Claim is we could actually write it as a product of these two partitioned matrices. Let's check that. This is what's going to make it work. Let's see, first row, first column would produce an A11. First row, second column would produce A11 times A11 inverse, A12 plus 0. Yeah, A12. Second row, first column produces an A21, right? Second row, second column, geez, that one's pretty involved, eh? We'd have A21 times this, A11 inverse, A12, sounds familiar. And then we'd add this times the identity. Wait a minute, I said we'd have what? A21 times this, that is this other thing. So when we do A21 times this entry, we pick up this term without the minus sign. Then when we take this times the identity, we add this to that other, this part cancels, we're left with A22, and the arithmetic checks. So this is a legitimate, that's a factorization in fact. So we've got A written as a product of matrices. You like these matrices? Yeah, I think so. This one's got an A11 in it. This one's got the Schur complement in it. That's part of the question. Hey, look at this. That's an upper triangular matrix because it's got identities here. So the determinant of that is the product of the diagonal entries. The determinant of this one's 1. So we can take the determinant of A as the determinant of this times the determinant of that. On this right-hand side, no matter how you slice it, the determinant of this thing here is 1. View it as upper triangular. You can also view it in light of some theory that we've had. We need some of that theory. Theorem 3.1.g said, hey, if you had a matrix partitioned up where you had either a 0, one of the partitions was a 0 matrix in the upper right, or a 0 matrix in the lower left, kind of like we do over here, then you can compute the determinant by taking the determinant of the parts along the diagonal, as it were. So Theorem 3.1.g, justifies us in saying the determinant of this partition matrix is the determinant of this times the determinant of that. Determinant of A11 times the determinant of the Schur complement, like we were supposed to get. I can similarly expand this one out as determinants, but the determinant of the identity is 1. Those disappear. We get the determinant of A is as claimed. Determinant of A11 times the determinant of the Schur complement of A11 in this matrix A. And that, let me double check. Yeah, and that's a content of section 3.4. So much more reasonable length section to get through. Thank you for your support. I will see you soon in section 3.5.